Welcome back. So, yeah, when I saw the weather reports this week, my head was about to explode. I said, if we're going to miss, we can't miss another lecture. So I'm glad that it was a non-storm this time. So I wanted to thank Pete actually and thank all of you for filling out. But I love the feedback. I always read the feedback and really get a lot out of the feedback. But we never actually had done a post-midterm feedback before. That was a great idea, and it was super useful to hear what you said. So we'll grade them very quickly. I think all is well. Don't worry if you felt like things went poorly. We'll figure it all out. And in general, I felt like, and this is easy for me to say, I felt like if you had come up here and I just gave you a blank piece of paper and there was no midterm, just the questions that you guys were asking on Piazza like the days before, I loved it. I mean, that's the value of the midterm. The actual taking the midterm is, it's the fear of the midterm that does the work. The actual midterm is kind of not the important part. So thank you for that, and I hope it was good. I've never actually been complimented for a midterm, right? And I don't expect ever to be. That's just not how it works. But I felt like we sort of rushed through the trajectory optimization, and I want to move on to the next thing. But let me just quickly show you. I found that. It's actually not that I found the videos, it's that I regained the ability. I found an SWF player that would work. So some of my locked up videos, I can play again. And there's just two little ones that I wish I had shown before. This is just the perching that I talked about last time. But the cool thing about it is that you can see the initial trajectory here. This is the trajectory optimization being animated as it's doing its thing, and that's something that I'm trying to throw in the new version too, is to have the callbacks so you can actually visualize the trajectory as it's being solved. And we talked a bit about the different, the shooting methods versus the transcription methods, and why would you put extra decision variables for X even though you don't really need them? We could just solve forward in time. One of the reasons is that I can initialize the X variables sometimes with very trivial solutions, saying, well, wouldn't it be great if the plane started over there but it went sort of in a straight line towards the goal, which is of course not physically real, but that's a good enough initialization that it can help the solver find solutions in times when if you just take an initial guess at at the control input, then it might have a harder time sort of finding its way to the goal. So here you go. It finds its dynamically feasible solution, and then off it goes. And it's it's so fast you have to slow down the solutions. And then the other one that I like that sort of shows that is the collision avoidance. This is like the quadrotor example I showed, and that's a static image. Let me try this one. Just watching the trajectories morph around and figure themselves out to get around polygonal obstacles in this case, right? But there's actually a bunch of things you find out when you do this, and if you watch, it showed a little bit of the signs of the kind of things you get to watch for, but you start watching the solver sort of struggle to converge sometimes. Those oscillations at the end mean that there's some numerically non-ideal things inside my solution. This one also, there's another feature that goes by quickly, but it actually resamples and resolves one last trajectory optimization with denser time samples at the end. So it does a coarse plan that avoids the trees to begin with, but then because it's only checking collisions at the points, I do a denser trajectory optimization seeded with the initial trajectory optimization to clean it up and then go. So these sort of visualization tools are actually super useful for understanding what the solver is doing. Okay, but to some extent, collision avoidance. Well, I'll show one more before I go. I'll leave it up for a second. So collision avoidance is I don't want to say it's for wimps, but it's you know, like you shouldn't, you know, real robots should touch the world, right? You know, like the robots I want to be involved with shouldn't just avoid collisions always. They should, you know, they should do mechanical work on the world, right? They should reach out and touch it. They should walk on it. They should do all these other things. And we haven't given you the tools yet to deal with that complexity of interacting, actually physically interacting with the world. And that's the goal for today. And you know, this comes up in spades in manipulation. It also comes up in walking. Those are the canonical ones. I like to do walking first for a couple reasons. One of them is because I think there's a nice way to view control in terms of, you know, stabilizing a fixed point. We've talked a lot about that. We thought about Lyapunov functions, optimal control objectives for stabilizing a fixed point. That's not as natural. You can make that story in manipulation, and you should make that story in manipulation, but oftentimes manipulation is more, it's more about doing something once. In walking, there is a natural extension of stability, the concept of stability. So it's not about, I mean, of course there's standing still, but we're going to do better than that. You know, walking now, we're going to get to the point where we're trying to talk about the stability of a periodic solution. Okay, so one of the key ideas today is actually extending our ideas of stability and stability analysis to talking about limit cycles, which is the stability of a periodic solution of a dynamical system. Okay. You know, the other reason that I like to think about contact in the language of walking first is because there are some really beautiful, simple models that are kind of like our acrobats and cart poles that we can really dig in and understand, and they're very satisfying. And then they're sort of representative enough that they've made real robots work. Thinking about it like that. And manipulation, it doesn't have quite the same. I mean, there's some pushing and other things are good, but it's not quite as satisfying. I think the simple models are stronger in walking. So today we're going to try to do sort of, you know, the acrobat cart pole type equivalents of walking models and the tools, you know, contact mechanics and limit cycle stability to get there. Okay, so I showed you, you know, in the very first lecture, I showed you the video of the passive dynamic walker, right? This is work by Steve Collins when he was working with Andy Ruina at Cornell, and this is the most impressive passive dynamic walker ever built to date. It's it's got no motor, no controller. It's basically a glorified slinky. You put it on top of a ramp, you give it a little push, and it walks like that. And we'll talk about humanoids again, but you know, humanoids, remember, walk like this, right? And by most accounts, this one looks more natural, and it's certainly more energy efficient. It doesn't take any energy except for gravity. And it sort of just looks like someone taking a stroll through the park, right? So the goal is to try to understand that. And there's kind of a cool history behind that. So I dug up this old video. This is Tad McGeer. He's actually an aerospace engineer who came in and dabbled with walking robots for a little while and had an enormous impact. It was sort of along the time that Rayburn started building his hopping robots. This was sort of the other big thing that happened to walking that just kind of blew people's mind. And I had no control of the audio, so let's see how it goes. So this is Tad.
This familiar toy is a passive dynamic walker. With energy supplied by falling weight and the right start, it settles into a steady walking cycle sustained by an entirely passive interaction of gravity and inertia. This machine is also a passive dynamic walker. For that matter, I may be a passive dynamic walker. As you'll see, our gaits are quite similar. The camera was running the day when the analysis and my intuition were brought conclusively into line. Oh, God! Those few steps convinced us that we had the dynamics right. The reason the machine failed was a problem called knee bounds. So for later experiments, we went to a set of mechanical catches, and the next sequence shows our first trial with those. I guess they work.
So, that work, you can see he's got pairs of legs on this robot. We call that the McGear walker, and that's so you don't have to worry about falling over sideways. But he's got knees and feet and curved feet, and it's actually really hard. I mean, I worked on these robots in my thesis work, and it's very hard to sort of get the curvature just right and the debouncer and the knee mechanics. So the way the knee works, okay, it's actually a suction cup with a hole drilled in the back and a screw in that hole, and you tune the leak rate of the suction, right? So it's like it's got to go and stick so it doesn't bounce back and everything, but then it has to kind of release in time for it to be, it's not fun tuning those things up, but once you get it, it's beautiful, right? And then Steve's was the 3D version. That was the first really dramatic demonstration of a 3D version of a passive dynamic walker. But what's magical about this was that these very simple systems, Tad even, in his initial papers, he wrote simple models of the walking behavior that really helped us think about, generated a lot of the simple models for walking and inspired those. And in fact, there's a whole history of these sort of simple models. This is Art Quo's animation of a simulation of the Tad McGear walker that it was just, there's a burst of creativity about understanding the simple mechanics of walking, and I want to give you just a little bit of window into that today. So again, the stability of these things are not the stability of a fixed point, but what we'll see is that we can take some of our ideas about stability and fixed points and extend them to the case of talking about the stable walking, okay? So the idea there is to progress from the stability of a fixed point to limit cycle stability. So a limit cycle is just it's just a stable periodic solution of the dynamical system. So given x dot equals f of x, x star of t is a limit cycle. Locally or globally stable. So there is some period for which this is true. So for instance, if you take, limit cycles are really, the term limit cycles are almost always reserved for periodic solutions that are stable. So for instance, the undamped pendulum, the homoclinic orbit, or any of the orbits of constant energy on the undamped pendulum would typically not be referred to as a limit cycle because they're not stable. If you were to perturb the system in energy, it would not return to the original cycle. But if it is stable, we can talk about limit cycle properties. So how can I write stability? So we mentioned very quickly the stability of a trajectory. Right, we could say that you'd like to say something like x of t minus x star of t. You like to say somehow that the limit of that as t goes to infinity, you want that to go to 0, right? If I've got some trajectory like x star of t, and I've got some other initial condition, and I start simulating from that initial condition, I'd like for these two things to come together as t goes to infinity, right? But the stability of trajectory, we talked about this a little bit because we had a question about it, but this requires not only that they converge in space, but also that they converge in time. So this, x star of t is moving forward at some time, and this, for it to be a stable trajectory, actually has to match both in time and in space. Okay? It turns out that's going to be too much to ask for most of our periodic solutions. So it can be true of any trajectory, but it's especially relevant when I now have a cycle. Let's call this q and q dot, for instance. Now let's say I have some sort of periodic solution, x star of t. That stability is still perfectly valid. I might have it here, but there's it feels that dependence on time feels even more artificial now, because that says if I had a solution that's on this trajectory and a solution that's also on this trajectory, that the system, in order to be trajectory stable, those two have to somehow come together. But if it's on the periodic solution, I'd actually expect it to just continue to stay a little bit apart, for a long time and keep moving forward. So one of the things we have to do is improve our notion of trajectory stability to handle this case. And the idea in limit cycle stability is to do something like this. Does that make sense? So for I've got my nominal trajectory here. Now, the thing that I'd like to get closer is I'd like to somehow I'm allowed to look over any points on this manifold, on this trajectory, find the closest point, and that's the distance that I'd like to get smaller. I'd like to drive that to 0 as time goes to infinity. And if this property holds, then this, and it's periodic, then this is the stuff of limit cycle stability. And in general, this is an orbital stability, it's called. So in fact, all of our walking models, if you tried to prove stability of this type, you would fail. But if we're going to be able to show for some very simple models where we can write the algebra on the board, that we are going to be able to show stability of this form. Okay? In many cases, this is a better thing. It's a harder thing to reason about, but it's a better thing to ask for. And we could even stabilize our perching plane with this, asking for this type of stability, and we'll get back to that at some point too. Okay, so I want to give you an example of limit cycle stability and then some of the tools for testing for it. Independent of contact, because that's a perfectly valid concept with or without contact, but it's interesting if there's contact. Okay, so here's a simple example. One of the canonical oscillating periodic solution sort of dynamical systems. So this is governed, it's just a second order differential equation. that is, let me write it like this. Okay, so that's the governing equations of the van der Pol oscillator. And if you're mechanically inclined or you like the physical intuition, when I see this, I look at this and I say, that looks, if this was sort of, so mu is just a positive scalar constant, okay? That one's a little ugly, but if I look at it like this, it just looks like a second order damped system, spring mass system, for instance. And now I see that with this added, it looks like a second order spring mass system with state dependent damping is a fair way to think about this. In particular, so I'd expect a linear second order system to sort of go like this, and if it was damped, it would of course go down towards the origin, so that's not a very good oscillator. That's not what we want. But if I make this sort of a state dependent damping, where notably if q squared is less than 1, then it's actually negative damping. It's going to flip the sign on this and put energy into the system, right? But when q squared is greater than 1, then it's going to act like a standard damper, right? Okay, so the idea is you've got some, q squared equals 1 sort of location here, and you'd like to have the trajectories spin out when you're inside that. And then, but when you're outside, you'd like to come back in. And in fact, the result is that you get a beautiful oscillation in the system, Q versus Q dot, and it looks something like this. It goes. This is sort of my, this becomes the stable, we'll see that it's stable, periodic solution. It's not quite that lumpy. But, and when you're inside, trajectories will go out until they converge on that cycle. And when you're outside, the trajectories go in. So you can imagine typing those equations in, simulating it, and watching the system going around like that. But how can we actually, so I think intuitively with a simulation sort of analysis, you can pretty quickly convince yourself that there's a stable solution. That's a periodic stable solution. But we need to develop some more tools if we want to be a little bit more careful about that, right? So how do we evaluate stability of a limit cycle, right? We've had tools about linearization for local stability. We've talked about the Lyapunov methods. We've got all these, and all of them are going to apply again. But we need some help. There's a trick that we have to do first. Because there's some fundamental challenges here, right? So I don't even know how to represent x of t, x star of t, right? So how am I going to do math if I can't write down the curve that describes here? I can't integrate that in closed form. I can get a numerical approximation of it, but how am I going to somehow talk about stability to that, that thing if I don't even know what I'm trying to be stable to? Okay, so the key idea that allows us to convert limit cycle stability back into fixed point stability. Okay, and the idea is if you can find, if you're happy, if you're able to, upon inspection, understanding something about the dynamical system, pick a lower dimensional surface. In this case, I'll just choose this axis. And instead of examining the whole solution of the dynamical system in time, if I only examine the properties of the system as it crosses this plane, then I have now a discrete dynamics, right? Because it jumps from here to here to here, or whatever. But I'm able to start talking about the discrete time system that lives on this surface and asking about fixed points of that discrete system in order to say something, and we're going to understand, when that relates to the stability of the original system. So this idea, this surface is called the surface of section, typically. And if, in general, if x lives in Rn, you'd like that the surface of section to be n minus 1 dimensional. Let's call it S. S is in. Also, in order to have the ability to say something rigorous about the original higher dimensional system, you'd like to be able to guarantee that any time the system starts in that surface, it will eventually return to that surface. Okay? And to make sure you actually leave S, there's a requirement that it's got to be transverse to all of the vector field of the original system. So none of the vector field, it doesn't have to be perpendicular everywhere, that would be too much to ask, but none of the vectors can be along the length of the trajectory, right? So this says if I start in S, I'll leave S, and this says I'll come back to S. And that allows you to then talk about the map from one visit of S to the next visit of S. And this is called the Poincaré map. And so this is the lower dimensional,
Sorry, can you write a little bigger on the bottom?
Yes. How much of it is hard to read?
Just the two things you wrote, yeah, so that and the map.
Yes. So this is the Poincaré map. He's an important guy, so I'll write it big. Poincaré map, and then I just said that XP in this is the lower dimensional. Thank you for asking for that. Okay, and so I'm not going to give you the harder versions of the theorems, but you can find them if you like. But the Poincaré-Bendix theorems talk about your ability to make statements about the original solution by examining the dynamics on the map. And this is the version I think you need. It's just as long as you have those properties in a rigorous sense, then you can say, then you can infer if you find a solution that is a fixed point of this system, and that fixed point is stable for this system, then it will imply that there exists a stable periodic solution of the original system. Okay. In this example, S is defined as Q equals 0, Q dot greater than 0. And that's going to work out. So how do you compute, or how do you work with P? I mean, so if I have P, then I can start asking about its stability. So we haven't done as much discrete time stability, but I think the ideas are clear, right? XP star, it better be the case that XP star equals P of XP star, right, to be a fixed point of the Poincaré map. You can ask about the local stability of that fixed point, right? Be a linearization. If you get partial P, partial XP, that gives you a system that looks like XP of n equals n plus 1 equals A of XP of n, right, where A is this gradient. And then you can ask, so what are the conditions on A? Right? In continuous time, we need those eigenvalues to be strictly negative. But in discrete time, you'd like the eigenvalues to be within -1 to 1, right, inside the unit circle. So all of your standard tools for fixed point analysis start working. Of course, it's in the unit circle if you have thought about complex eigenvalues and the like, but I won't dwell. Okay, but the only problem that we have here is that I have to have a closed form expression for P to do that work. And I don't even for the van der Pol oscillator, which is one of the simpler examples. Yeah?
What's the difference between Poincaré maps and just the dynamics of the system?
So the Poincaré map takes away everything that's not on this line. So it's a view of the world which just says, if I started here, on the next step I'll be here. On the next step I'll be here. On the next step I'll be here. Dot, 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 dot. And I'll converge to this. Or if I'm out here, then I'm going to go here, 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 here. It's a summary of the entire system, but only at this point.
Oh, wait.
On this plane, sorry.
Surface or any point on the plane?
It says it's the dynamics that from one visit, if I start on that S at XP, and then I simulate until the next time I visit S, which is I'm guaranteed to hit that at some point, that's my XP n plus 1.
And do your XP of n's have to be on the surface, or could they be anywhere on the QQ?
They're on the surface.
Okay.
Yeah. That's what I meant by saying that they're in this lower dimensional space. So a lot of times, because of this Poincaré analysis, there's a few simple examples where you can get P in closed form, but there's not many. So a lot of times, the tools you need to work with this become numerical pretty quickly. Okay, so you end up with numerical versions of P And you can take gradients of P numerically, and we'll talk more about the numerical methods of contact and limit cycles next time, but I want to give you the simple examples today. Okay, so that's a frustration, is that you have to typically do this, this work numerically. And then we can talk about local and global stability of limit cycles too, by asking about, for all initial xp, do I converge to a fixed point or not? So let's think about it for the van der Pol oscillator. I will cartoon it as if I had sampled from it numerically, but so if I do q dot at n versus q dot of n plus 1 is my Poincaré map, right? And in fact, I restricted myself to only q dots greater than 0. Okay, so I'd like to be able to make a plot now of, given q dot at n, where does it come back to at q dot n plus 1? Okay, and remember all of our graphical analysis of continuous time first order systems. You could just draw the arrows, based on whether it was above or below the axis. In discrete time systems, you can do basically the same kind of thing, but what's relevant is not whether it's above or below 0, but where it falls relative to the line of slope 1. All right, so this is. Why is that? Because a fixed point on this map is when, I start at Qn, and on the next step I'm Qn plus 1 equals Qn, right? So this is a fixed point on the map, is if it's on the line with slope 1. Okay? Now if I start plotting this curve by evaluating the van der Pol oscillator, I'll start making the plot. I'll just say, if I started here and I go around, where is it going to be? If I start here and I go around, where is it going to be? I'm going to just run a simulation until it hits again, and what do I get here? I get a curve that at 0 is 0, so there is a fixed point at 0. And then it starts going up because for small q dot n, it increases, right? And then it goes through this, and it decreases like that. Okay, so that's what the numerical evaluation of the Poincaré map looks like for the van der Pol oscillator. And this is, now you have to, in order to graphically investigate discrete time system, you end up thinking, they often call it the iterated maps, right? Because whereas in the continuous time system, I could just say, there's an arrow here, there's an arrow here. Discrete time systems don't have the flow, they jump, right? So let's just think about how that works. So, if I started here, then I'm going to, so if I started here, then on the next step I'm going to go up to here, right? And then the way to think about how's that going to go on the next step is I project now to this line of slope 1. And then I'm at this next state, I go up to here, I project, I go up to here, I project, and you can you see these staircase diagrams. This one, if I started here, I would have gone like that. Okay? Similarly, if I went here, then I'm going to go, on the next step, my value is going to be q dot n plus 1. If I want to project that down to the axis again, I can do that by drawing it to the line, here, 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 here. Okay? Does that make sense? This horizontal line is just me projecting it down to the very next q n plus 1. Okay? And sort of you can convince yourself for this particular example, and you can convince yourself more rigorously with linearization or Lyapunov type analysis, we'll do in a bit, that this will actually ultimately converge to that fixed point, and that is a stable fixed point. Okay? So fixed points are stable if they're within -1 and 1 and -1. Right? You can get funky things, right? If I had a slope that was less than -1, then what happens in that example? If I had a point that had a slope like this, then my iterated map would go like this, right? Boom, 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 to here, boom, boom. It would sort of blow up to the outside, right? Cool. So just by graphical inspection of this, we get our intuition that there is a fixed point here at the origin. It's an unstable fixed point. Neighbors, solutions neighboring that fixed point will leave, right? And we have a fixed point here, which is the limit cycle we expected, that is a stable fixed point. And trajectories there will converge. And the region of attraction of that fixed point is going to be all x except for that origin. Right. Does that make sense? My kid's trying to FaceTime with me. If she keeps calling, it could be important, and I'll answer, but I'm going to assume not first. And if Hayden, if you ever watch this, I apologize. Okay, is that clear? You can ask. What's up?
How do you extract QMF plus 1 using the stair steps thing? Why is that related?
Yeah, good. That's like totally. If you don't get that, then it doesn't make sense. So what am I trying to do here? So you understand that if I'm here, I can evaluate what Qn plus 1 is going to be, right? And what I want to do is now say, okay, I've got this one. So where does it land me? It lands me over here, right? There's just a geometric way to do that, to make that projection. And I could look this up. I could measure this distance. I could put it down here. A graphical way to do that is just to say, well, let's project it to the 1, 1 line, and that tells me where I should have ended up. Right? All I'm doing is measuring that and putting it here, and I'm doing that by slamming into the line of slope 1 and going down. Okay, so for our next trick, we're gonna do limit cycle analysis, graphical limit cycle analysis of a walking robot. Okay, we're gonna need to do contact mechanics to do that, and I have to admit that so this is a 2D plot, 2D system. I have exactly one example in the whole world where you're going to be able to draw the limit cycle analysis of a walking robot, because walking robots are too complicated almost always. But I've got one example where we can draw it, we can understand it, okay? There's sort of two, but it's some tricks to play it to get the running version. Okay, so that's limit cycle analysis. The other piece I promised you'd need is to understand something about contact, okay? There's lots of ways that we can talk about contact. Okay, so let's say you're a robot foot and you're about to slam into the ground. We know, we did quickly, we said there's the equations of motion. Do you see what that is? That's just a foot? Okay. Some people were kind of like this. So that's a foot, it's coming down, it's about to hit the ground. How do we write the equations of motion for that? I'm not going to ask you to derive them or anything, but there's a bunch of different ways to model that dynamics, and it's going to have implications on our ability to do analysis. Okay, so let's even keep it simple. Let's say I've got a particular point on my foot that's going to hit first. How would I model that contact? There's a bunch of different ways people do it. One of them is to have a compliant contact model, where you basically attach a spring here, if I were to zoom in on that. I basically attach a spring between the ground and my foot that's penetrating, and say there's a force pulling up on the ground that's trying to keep me out of penetration. And that's actually a pretty good, maybe you even, there's some friction, looks like a damper inside that too, if you like, a dash pot. And that's actually a very good, I think, model of, it's a pretty reasonable model of the way contact occurs. You also need to do something for friction. We'll talk about that in a minute. But the problem with that is that it stinks for numerical, it definitely stinks for board work, and it stinks for numerical reasons too, because in order to have my, let's say a 400-pound humanoid simulated, so its foot doesn't go through the ground, you have to use a really stiff spring here. And suddenly then my dynamics have a very, ends up generating what are called stiff dynamical systems. So you have a very different sort of natural frequency of my dynamical system when I'm in contact versus when I'm out of contact. And this becomes, you have to integrate very carefully to sort of simulate that spring accurately. And this is actually one of the reasons why robots sometimes blow up in simulation and things like that, is because you have a very large set of gradients that happen when you occur and penetrate the ground. Okay, so there's an alternative, which is, so this is sort of the spring models. The alternative is rigid contact. Where you say that the foot will never penetrate the ground, okay? But, and so that's nice. It seems like our foot doesn't penetrate the ground. But now, in order to have, if you had a velocity that was greater than 0 as you were coming towards the ground, and then all of a sudden it has to be 0, otherwise you would have penetrated the ground, that means that there was an impulsive force that happened at the moment of collision that you have to start dealing with. So you really have to deal with instantaneous collisions. I apologize, but my daughter's calling me again. Let me just make sure she's okay. I'll be right back. Take 2 seconds. Hayden? Hayden, I am teaching my class right now. Is it an emergency?
Hey, rest the mic.
Okay, good. Sorry. Sorry. We'll have a conversation over dinner. Okay. So there's an extra complexity here that we have to deal with the moment of collision. Okay, and but we can deal with that. Okay, so what happens here? So basically now, in this case you have a very stiff but continuous time system. Okay, in this case we have something that's called a hybrid system. Because it's got continuous time dynamics, but then a discrete event that happens as soon as the foot hits the ground that we have to account for, so it has both continuous and discrete dynamics. hybrid is like one of the more overloaded words in the engineering world, but this is how we use it. It's not gas and electric or anything. Okay, so let me tell you about let's put all this together, and I'll show you some of the more details of the rigid contact in the example of our simple walking robots. Okay, so best example ever, the only walking robot that you will ever completely understand is the rimless wheel. I know. Okay, so in fact, this is from Tad McGear's original paper. Okay, well, not the simulation. This is the SWF that I was locked forever away. But this is, imagine taking a bicycle wheel, removing the rim, leaving only the spokes. For simplicity, we're going to put mass only at the hub. So it turns out to be the simple pendulum, basically, in its dynamics. Now you give it a little push on a ramp, and something magical happens. Okay, it starts falling down the ramp in a beautiful way. Okay, so there's two things we're going to think about here. Every time the foot comes around and makes contact with the ground, it loses some energy because it's going to have a rigid contact. We're going to assume that it's an inelastic contact and energy is lost into the ground. Okay, so it dissipates energy every time the foot hits the ground. Otherwise it'd be bouncing all over the place. Okay, but it gains a little energy because we put it on a ramp. So it's converting potential energy to kinetic energy. Magically, beautifully, just like in this example, and just like the return map that's under the board, those systems are going to balance into a stable phenomenon, where if it's moving too slow, it speeds up. It gains more energy from gravity than it loses from collision. And if it's moving too fast, it slows down. And it ends up, you can sort of see it in this. This is the slow down and then speed up example. I'm sorry, this is going fast and then it slows down. It ends up going into a stable periodic solution that will go forever. And that is the simplest walking model. There's another simple walking model that has legs with toes that are basically have no mass and they can swing around, but this is my favorite one. Yeah.
Wait, why did it slow down in that example? Like, or would have been before? Would it not converge on something stable? Or something that's like the same, I guess, same Q dot every single time? I think that's what I was surprised with.
I'm going to give you a good answer for that over the next few derivations, but I'm going to use this to sort of, dig in, and we'll show what the contact model is, and we'll show what the return map looks like, and you'll see it balance. Pretty cool though, right? Okay, so let's do the rimless wheel. So we're going to put it on a ramp. I'll call the ramp has slope gamma. Okay? It's going to be a that's right. Okay. You can have more or less legs, but I'm going to write the interleg angle as 2 alpha. Because you're going to see that half that angle is going to appear lots of times in the equation, so we'll just call that 2 alpha. And I'll call this angle, the coordinate of the pendulum, we'll call that theta, okay, which is the angle from vertical. So. So it's, you know, equations of motion are going to be identical to the pendulum in cases, but except for the offset of pi. And theta equals 0 is the upright. And it's got, you know, the length L, again, mass M. Okay, so our modeling assumptions that's going to keep this nice and tractable is we're going to assume infinite friction, okay? Did someone say that's what I thought? That's good. No slip. Okay? So that's a nice thing. What it means is that once I've touched down, it's still the case that I'm only allowed to get force in this direction. The contact forces are only going to be in this direction. I can't pull on the ground. Okay, but we're going to see that, well, you could, maybe I won't actually derive it, but that condition is going to be held always. So mathematically, we can think of this as just having a pin joint. Okay? That's going to be way better than having to think about, you know, penetration and stiff springs holding my foot in place and slipping as another, you know, sort of different mode of the system. It's much cleaner to have this. Okay, and then as the dynamics come around, we're going to assume when this foot hits the ground, we have an instantaneous inelastic collision. And you know, this inelastic assumption implies that there's no bouncing. And in practice, it's going to give us the ability to, we're going to realize that there's an instantaneous transfer of support. So when I come down, I'm going to connect with this foot. It's going to bang in here. It's going to stick to the ground because it's inelastic and it's not bouncy. And at that exact same instance, this foot is going to become free from the ground. As long as my foot never goes under the ground, I will see that my assumptions were correct, but basically there's going to be an instantaneous transfer of support from the foot being there, and then boom, there's an event that happens, and suddenly I have a pin joint here and there's no pin joint there. Okay. Okay, so if I start plotting the orbits of this system, again, it looks like a pendulum, so we should have a lot of familiarity about it. Theta versus theta dot. But now at 0, this is this part of the eyeball, right? Okay. There's a couple notable things, right? So this is my familiar stuff. Okay. Something dramatic happens at gamma plus alpha. That's when the foot can hit the ground in one direction. That's the angle at which, boom, I hit the ground on this foot. And then there's another place, if I were to go uphill, bang, I'd hit the foot on this. I hit that foot on the ground at gamma minus alpha. Okay. And in practice, we can start understanding the dynamics of this system. It's going to have trajectories that look like this. They're going to bounce around, for instance. the interesting trajectories, the limit cycle trajectories that I showed you that walking of, the way it looks is it starts somewhere up here, it goes down and back up, and then boom, there's a collision, an instantaneous transfer of support. It comes over to here, okay, and it's reset again. At some point, there's a stable cycle of the dynamical system that we're looking at that does something like that. Is that clear? So this straight line back is just an instantaneous jump, boom, back to some other place where your foot is now, the thing that was your back foot becomes the thing that was your stance foot becomes your back foot, right? And then you start falling again, and the energy gained from going downhill is because this thing is shifted by gamma, right? So if it was completely symmetric, if gamma is 0, then it'll go down and come back to the same height it was before, and you would have gained no energy. Okay, but because this is shifted, I didn't draw it very well, but it'll go down and actually have time to come back to a higher velocity than it left, because that's shifted, right? It's asymmetric. And then it loses some energy on the impact, so when it gets put back over here, it drops down a little bit. Otherwise, it's just the pendulum, right? Now you can see why I like pendulum so much. All right, so let's the stance dynamics are really just the pendulum, so I don't need to do that again. And we can imagine even writing an algorithm that would, while simulating the pendulum, constantly check for whether the angle has hit this limit and has to do something different. But the question is, let's try to figure out what that contact model is in order to understand what that projection needs to be. Yeah?
Why is it the other way around? Because this thing is going, you should increase your, increase the top. Okay, never mind, that was a bad question.
It wasn't a bad question, but it was a bad drawing. I think if I had drawn it a little better, you'd see that it started low and went high, because that's shifted. Yeah.
You're saying it's shifted, you just mean that gamma's not 0.
Gamma's not 0. If gamma's greater than 0, then you can gain energy. Yes. The gamma equals 0 case is, it just does this. So that would, which is fine, but it kind of goes like this, boom, boom, boom. And on these pictures, it would look like a tick-tock around here until it came to rest either here or sort of simultaneously there and there. And then you get into some funky analysis there, because this model, as written, in that fixed point, is actually undergoing infinitely frequent collisions. Right? It doesn't actually stop until the frequency goes to infinity. There's the Zeno paradox there, which is a real thing in hybrid systems analysis. The same thing as, does the arrow ever hit the wall, right? We won't go there. We'll focus on the other part. Although it's the Lyapunov analysis gets around Zeno paradox. Okay, so what does the inelastic collision look like? So here's the picture you need to have in your head and the basic mechanics that you want. So I've got a robot like this. Let's say this stance, it's currently in this stance foot, and this foot is about to contact the ground. Okay? How do I figure out what the change in velocity of the system is going to be? So what happens at the moment of impact? There is no change in position instantaneously, but there is an instantaneous change in velocity. Okay, and the way to think about that is that right before the collision, use my multicolored chalk. Immediately before the collision, since this is this is rotating around this point, its velocity vector has to be in that direction, and its momentum, its angular momentum around that point, but its linear momentum looks like mv. Okay. Immediately after the collision, this foot's going to be in the ground, and it had better be that the angular velocity is now orthogonal to this. Okay? So the collision dynamics assumption of having all energy lost into the ground and having inelastic collision, there's still so energy is no longer a conserved quantity. You dissipate energy into the ground, but angular momentum around that point is still conserved. So you can write mv minus, which would be before the collision, mv plus after the collision. And our job is going to be to figure out what is the mv plus that is, has the property that the angular momentum before the collision, which we'll call angular momentum L before the collision, equals angular momentum after the collision. You can imagine much more contacted if you're if you're a hand grabbing an object and stuff like this, then the conditions become more complicated. In this example, inelastic implies just angular momentum conservation around that point. Okay, and it turns out geometrically, I mean the equations are all written out in the notes here, but geometrically this becomes the projection. Right, it can't gain any energy, so it really is this similar triangle example. So all energy that is pointed into the ground is lost, so it's equivalent to projecting up to the vector straight up, okay, around the ground. So it turns out that the derivation yields that L minus equals L plus implies that theta dot plus is just theta dot minus times cosine of 2 alpha. Sort of as a mental check, it's kind of fun to think about what happens as alpha gets really small. I have no losses. I'm a wheel, yeah, which means I forgot to take into account rolling friction, but that's okay. It doesn't normally roll, okay? And then if alpha gets too big, then at some point it gets weird, right? Because you have two legs, and so we try to keep alpha at least pi over 2. The four-legged rimless wheel doesn't walk very well, I can guarantee. Okay, so let's start playing with it, and you'll start seeing that even though I cartooned the simple version, there's actually a lot of complexity hidden in there about all the possible things that could happen. So here's a nominal walking gait like we just had. It speeds up and walks. Okay, or that one I think slowed down and walked. Here's one where I start fast and I'll see it slow down more dramatically. Okay. But now you can start thinking about more complicated cases. So I think I picked one that was very clearly speeding up. Oh no, this is the standing fixed point. So that one didn't quite have enough energy to go over the top. Okay. So what does that look like in my phase, in my picture here, right? The difference between those two solutions, right? One of them started with an energy above the homoclinic orbit and went around here and then ended up speeding up. The other one started off below and didn't quite make it around and came back and collided with the same leg, right? And then it ends up projecting the other way and it gets trapped in the standing fixed point, okay? And then you can actually, it gets quirky, but all completely revealed by the math. So if I go, start off -5, I speed up, I go up the hill, right? And I eventually come to rest. But if I choose initial velocity of theta dot equals -4.8, then look what happens. Let me do that again. It goes up, comes down, but it made it back over and starts rolling forward. Okay? So you can actually, the basin of attraction of the rolling fixed point includes solutions that start going uphill and then go back downhill. Okay? practice the basin, you know what, it's too hard to draw. I'm going to just show you the picture. The basin of attraction looks like this. Okay, so that's 0, 0. Okay, I chose as the Poincaré map the line, you know, basically picking one of these surfaces as a natural point to evaluate the dynamics. In this case, the dynamics are simple enough and they're energy conserving that I can actually solve for P in closed form. Sorry to be so dynamic, P. I can solve for P in closed form here, and I have a closed form solution for my update, which is just cosine 2 alpha. So this is the one time I have an analytical form for P. Okay, and the rolling fixed point here. So here's my line of slope 1. The rolling fixed point is up here. And it's got a region where if it starts too slow, it speeds up. If it starts too fast, it slows down. Okay? Stable dynamics. And the beauty is that you know, we can understand it here, but you actually get it on the bigger, more complicated robots too. The same thing is true as you're trading the natural interaction with, it's what Tad said, right? The natural interaction between gravity and collisions. Collisions take out energy and gravity adds it back in. And then the map, if you continue on going backwards, is you know, got this funky, this is what it looks like inside when you're trapped inside. So in the region sort of where you started between here and here, you have that line dynamics where it'll slow down and get stuck in the middle. Okay? And then there's another special case, but again, because this is shifted, if I started here, right close to this, I can actually go around, boom, come out a little bit above this, and end up going up into here. That was the rolling uphill and then coming back. And then there's the solution over here, where if I started outside here, I still lose energy every time. And then I end up in this regime, and if I ended up in that little segment where it could escape, then it'll end up rolling forward. And if I didn't, then I end up getting trapped in the fixed point. Now, oh, you can actually see the blue, good. So those stripes, that hatched region, is the region of attraction of the rolling fixed point. And you can solve it analytically completely as time, you know, as that goes to infinity. It's a contraction mapping every time. So that thing gets bigger roughly by cosine 2 alpha every time. There's more and more states that will collapse and get into that. So you can ask me, you know, okay, what happens with theta equals negative 2,000? This is what my kid would do, right? What happens if it was 2,426 radians per second? And I'll say, I know the answer to that. You know, it's either in this region or this region, and I know analytically. Okay, so this is a very general thing for contact. This is the same thing in manipulation. We're going to see the same thing. Sometimes you think about it with impulsive. Sometimes you use spring models, but the dynamics are the same thing. This is the time where we could really think about it in terms of long-term performance and stability, and we'll see the numerical advantage of doing that later. But we can go a little farther with this. So the rimless wheel is the only one I can plot in 2D, but there are plenty of examples that you can sort of incrementally get more and more impressive, right? So this is now the compass gate, it's called. It's the rimless wheel where I added a little mass now to the 2 legs, and I took all the extra legs away, put a pin joint at the hip. Now it's a double pendulum, okay? You have to ignore, you either have to make your legs shorten or somehow ignore the foot scuffing in the mathematical model. But if you do, then this system also has the same stability properties. The dynamics when you hit the ground are, you lose a little bit of energy when you hit the ground, you gain a little of energy as you fall forward. This has a stable limit cycle. Its basin of attraction is not nearly as big as the rimless wheel. This one can actually fall down, right? And boy, does it when you start building them. Okay, the curved feet that McGear had make the basin of attraction bigger, but harder to model. You can do it with point feet. It just falls down a lot. And yeah, we've had lots of outtakes where it's like, you know, our point foot walker fell to the ground, you know, it explodes in a million directions. Plenty of experience with that. Okay, and then it turns out you can go pretty far. So, yeah, check. I didn't have quite as nice of a movie of this. I didn't have vector graphics, but I can play it arbitrarily. This is a version that now goes even a little bit farther, still point feet. Big mass here, little mass here, but now it's got a knee joint, okay? Even that will walk stably. This one, though, is so fragile that you have to do numerical optimization to find any solution that stabilizes it. Okay? There's 2 impacts in this system per leg. So there's a 1 impact. I think I have the. There's a collision which happens when the knee goes straight and hits the guard. There's a second collision that happens when it goes down, it comes up around, okay, but it all works, right? It all still balances out. Okay, so you know, that's the basic mechanics of it. There's actually, the simple models have more virtue than just analytical or sort of conceptual tractability. They've actually yielded a few insights that carry over to the more complicated models. So, for instance, my favorite example is Art Kuo and Andy Ruina talking about the efficiency of having a toe off. Okay, so you'd like to think that you could do better than just smacking your foot into the ground every time, right? Asimov, actually, in the analysis we'll do of Asimov, we actually don't spend a long time talking about collisions because Asimov does a lot of mechanical work to put its foot down effectively at 0 velocity. Right, so it's like you're really walking, so you go, and it's basically so you can ignore some of those dynamics. But it means you have to put your foot down really slowly, and that's no good. So it doesn't have any notable dissipation at impact, but it's wasting tons of energy to put its foot down like that and stop itself from falling forward. So what's the right way to do it? Can you be more efficient by by doing something else? Okay, and this picture told a beautiful story. So what's the right way to save energy when you're walking? What's the right time to push off? Okay? If you wait until your heel hits the ground, you've already lost the energy, even though that sort of might be what you think of. You'd heel hit the ground and then your toe pushes off. It turns out that if you have a toe in the back, you can be 4 times more efficient in the limit of a simple walking model, and a dimensionless analysis sort of told the story. You can be 4 times more efficient if you push off just before impact. Why? Because you can use your push-off on this leg to project your momentum here, and then the collision only takes away this energy. And you can go like that, okay? So if you just, as you're walking along, just before impact, you push off. And this has guided the work of a lot of, even active orthotics, for instance, people that are trying to build orthoses to make you walk more efficiently, that they actually try to time, the easy thing to do would be to put one sensor on this foot, wait till you make contact, and then push off with that foot. Sorry, you got to do better. You got to predict that collision, and then push off just before if you want to be efficient, right? So there's really beautiful stories that are hidden in those simple models. And we're going to see the running equivalent of those models, assuming I could fit it all in. But yeah, there's another beautiful story about the running version of this too. Okay, cool. Happy spring break. We'll grade some exams. And any other announcements?
And we'll release more in the final projects.
Yeah. Yeah. So yeah. One of the things is the problem set ready to go? Or?
Yeah. Is the website problem?
Yeah.
That'll be after.
So a great thing to do over spring break is to think about what you'd like to do for your final project. And we'll be happy to answer emails and stuff too, but there's some examples already up on the website, and we're going to put more and more up. Okay.